Hey guys, welcome back. Today we're going to be doing 13.6 about conditional probability. So I know we talked about this a little bit last time, but we will do some more specifics today. So let's look at this problem right here. It says, suppose the probability of rain on Saturday is 40%. What is the probability that you clean the garage on Saturday? And then it gives us these two little pictures over here. There's a 90% chance you clean the garage. That's if it's raining. If you can see that little rain right there. And then a 50% chance you clean the garage if it's sunny. Okay, so if we think about this, you basically have two options here. You either it's going to rain or it's not going to rain. So let's look at each option individually. So let's look at this one here first. If it does rain, we know that's a 40% chance. So we're going to say that's a 40% chance that it does rain. If it rains, there is also a 90% chance that you clean the garage. So we're going to do 0.4 times 0.9. That's saying it rained. And remember, when we do probability and means multiply. And you clean the garage. Okay. Then you also have the other option that says if it's sunny. So because we have another option, we're going to add on. That's or. Or means plus. If it doesn't rain, which in this case is going to be 60% chance that it is not going to rain, there's a 50% chance that you clean the garage. So 0.6 times 0.5. And then we just multiply these together. So that'd be 0.36 plus 0.30, which gives us a total probability of 0.66, or 66% chance that you clean the garage. Okay, so that in a way was a conditional probability because your probability changes based on some condition, which in this case was whether it rains or not. So looking at this, it says in the solve it you may have calculated the probability that it rains and you clean the garage, and the probability that it doesn't rain and you clean the garage, and then added the probabilities together. That's exactly what we did. You can find conditional probabilities using a formula. We didn't really use a formula in the last one, but there is a formula that we can use. In the previous lesson, you found probabilities using frequency tables. For example, in the relative frequency table at the right, the probability that a sales representative had an increase in sales, given he attended the training, is 0.48 out of 0.8, because you're dividing by the column total. With respect to the probability, this would be a probability of increased sales given they attended the seminar. And to put that into our formula, we were doing the probability that attended the seminar and had increased sales. That would be the 0.48 divided by just the probability that they attended the seminar, which is the 0.8. Okay, so this brings us to the conditional probability formula that looks like this. Probability of B given A is going to be the probability of A and B divided by the probability of A. So an easy way to remember this is this line right here that means given. You can kind of think of that as a division line. And just know that P and A, the and always goes on top. And then you're always dividing by the second part here, what is given. Okay, that will give you your conditional probability. So it's probability of both happening divided by the probability of your given. So can use that to solve this one. It says in a study designed to test the effectiveness of a new drug, half of the volunteers received the drug, the other half received a placebo, a tablet or pill containing no medication. The probability of a volunteer receiving the drug and getting well was 45%. What is the probability of someone getting well given that he received the drug? Okay, so we want the probability, I'm going to write this out, of getting well given they received the drug, not the placebo. So this one we're going to do the and on top. So probability of both, I'm just going to put both so I don't have to write everything out, divided by the probability of what's given, which in this case is the probability of getting the drug. Okay, so it does tell us that the probability of receiving the drug and getting well is 45%, so we're going to do 0.45 divided by the probability of getting the drug. Well, it doesn't give us any other numbers here, but it does say that half of them receive the drug, so we're going to divide that by 0.5, and that will give us 90%, or 0.9. So the probability of someone getting well when they receive the drug is 90%. So 90% of the people that receive the drug, if they're sick, will get well. Okay, so that's conditional probability. Comparing conditional probabilities. Okay, so now we're looking at something a little bit less serious than sicknesses and drugs in today's world. In a survey of pet owners, 45% own a dog, 27% own a cat, and 12% own both. What is a conditional probability that a dog owner also owns a cat? What is a conditional probability that a cat owner also owns a dog? Okay, so let's do the first one. It's going to be probability of the dog owner also owns a cat, so you're given that they're a dog owner. What is the probability that they also own a cat? So probability of a cat given that they already own a dog. So that's going to be probability of both divided by probability of having a dog. Okay, so this one, both is going to be 12%. And actually, you can just do 12 if you don't want to do 0.12 because you're dividing. So as long as you keep it consistent on the top and bottom. Probability of owning a dog is 45%. So 12 divided by 45 comes out to be 0.26, repeating, so we'll just say 0.267. Okay, and the second one, we're basically just reversing that. Probability that a cat owner also owns a dog. So now we want to do probability of dog given we know they own a cat. Okay, so again we're going to do the probability of both, which is our 0.12, but this time we divide by the cat percentage, which is 0.27. Okay, so 12 divided by 27, which is 0.4 repeating. Okay, we're about 44%. Okay, so cat owners are more likely to own a dog than dog owners are likely to own a cat, if that makes sense. So they are not commutative, is that the word? Commutative, yeah. So when you reverse them, it doesn't stay the same necessarily. Sometimes it can, but not always. Okay, because probability of B given A equals the probability of both divided by the probability of the given, and then if you want to solve for P and A, you would just multiply this equation by probability of A. That way those cancel, and that gives us this formula right here. Probability of A and B is the probability of A times the probability of B given A. You can use this formula of the conditional rule when you know the conditional probability. You can also combine conditional probabilities to find the probability of an event that can happen in more than one way. So this one, we are going to be using a tree diagram. So let's give us some room up here. Okay. The college reported the following based on their graduation data. 70% of freshmen attended public school. 60% of freshmen who attended public school graduated within 5 years. So that's going to be your conditional right there. 80% of other freshmen graduated within 5 years. What percentage of freshmen graduated within 5 years? Okay, so we're going to start by making a tree diagram. Alright, so the first thing we want to do is we want to say whether they attended a public school or other. Okay, and we know that 70% attended the public school, so this would be our 70 here, which means that 30% would be in the other category. That way it adds to 100. And then your options, we're looking at, did they graduate within 5 years? So I'm going to say less than or equal to 5 years. Or maybe it took longer than 5 years, so greater than 5 years. Or maybe they didn't graduate, so I guess maybe that's not the best label for that, but that's okay. And then the same thing with the other. So within 5 years, or I'm just going to say not within 5 years. Okay, and then if we look at this part right here, it says 60% of freshmen who attended public school graduated within 5 years. So this is 60%, which means that 40 would be the complement of that. And then the next one, it says 80% of other freshmen graduated within 5 years. So this is be 80 here, and this is 20. Okay, so only these have to add up to 100 together, and these have to add up to 100 together because those are conditional probabilities. They're given based on some condition. So the whole thing doesn't have to add to 100, just each individual part of the tree, I guess. Okay, so then we want to know what percentage graduated within 5 years. So we're actually looking at this number and this number here. So we don't really care about these ones. Okay, so if we want to know how many public graduated within 5 years, we would take our 0.70 here. We know 70% go to public school, and 60% of them graduate in 5 years. So we're going to multiply those together. 0.7 times 0.6. Then we'll do the same thing with this. 0.3 times 0.8. We're going to add those together. So that gives us 0.42 plus 0.24, which is 0.66. So again, I think that I paused it somewhere on accident, but anyway, you're just going to multiply the 0.7 here with the 0.6 here, the 0.3 here with the 0.8 here, and then add those together, because those are your two options. Okay, and it comes out to be 0.66, so about 66% graduated within 5 years. Okay, so one option is your tree diagram like that. Okay, we can also think of each piece individually, kind of like we did with the rain and the sun. So looking at A here, it says a soccer team wins 65% of its games on muddy fields and 30% of the games on dry fields. The probability the field is going to be muddy for their next game is 70%. What is the probability the team will win their next game? Okay, so the field is either muddy or not muddy. So if it's muddy, there's a 70% chance that it's muddy. So, why is it not working? Okay, 0.70% chance that it's muddy. And if it's muddy, we know that there is a 65% chance they will win. So this is the muddy win. Plus, now we have to do the dry win. Okay, so if it's 70% chance it's muddy, that means there's a 30% chance it won't be muddy. So 30% times, and they only win 30% of their games on dry fields, which is kind of weird, but it's alright. So then we're just going to add those together. So that gives us 0.7 times 0.65, 0.455. Plus, that's going to be 0.09, which comes out to be 0.545. So there's about a 54.5% chance that they win their next game. Okay, if the probability of the field being muddy increases, how will that influence the probability the soccer team wins their next game? Well, you can see that they win more frequently on muddy fields, so if they're actually better if it's muddy, so if the probability of it being muddy increases, then their winning should increase. Probability. Okay. Let's give ourselves some room again. If probability B given A equals probability of B, then the statement probability of A and B equals yada 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 simplifies to just probability of A times probability of B, which is true only if A and B are independent events. This leads to another way to test for the independence of events. So you can test if A and B are independent events if and only if, which are biconditional there, probability of A given B equals the probability of A, and the probability of B given A equals probability of B. And those both need to be true, so you have to check both of them. Okay, so looking at this one, two-way frequency table shows the number of juniors and seniors in a school who hold part-time jobs. A teacher selects one junior and senior at random. Consider events A and B below. Are the events independent? Use probabilities to answer your question. I think I am not on the right side because I don't have these events. Okay. Oh, okay, so let's do this one. So here's our two events, A and B. Event A, the selected student is a junior. And event B, the selected student does not have a part-time job. So Okay, so I've rewritten the what we need to check on the top. So probability of A given B equals probability of A. So first let's figure out what the probability of A is. So probability of the student being a junior. That would be, there's, let's see, 175 juniors out of 356 total. Okay, and that simplifies to be, so I got 0.4915, and then it keeps going on, but I just cut it off there. Let's look at the probability of B, which is going to be the selected student does not have a part-time job. So no part-time job would be 190 out of 356, which comes out to be 0.5337. Okay, so now we need to look at your conditional probabilities. So probability of A given B. So probability the student is a junior, given they do not have a part-time job. So whatever you're given, that's what you're going to divide by. So we're going to divide by the 190 total. That's how many don't have a part-time job. Probability they are a junior is 104 out of 190. 104 out of 190. 0.547. Okay, so we can already see that this is not equal to this up here. So at that point, we don't need to do the other step because they both have to be true. So we can say that these two events, A and B, are not independent because this does not equal this. Okay, if those two were equal, then we would still have to check the probability of B given A. Okay, but we're not going to do that because we don't need to. Okay, next one. That was it, actually, I think. Oh, yeah, I just switched my slides for some reason. Okay. Yeah, so that is it. Make sure you guys do the Canvas quiz about conditional probabilities, and I will catch y'all on the next one. Au revoir.